traveling salesman problem. What is the traveling salesman problem? So you are given some cities. Here we have 4 cities: A, B, C and D. The salesman has to start from a city, visit every city exactly once and come back to the starting city, right? And this travel will cost some, it may be time, it may be amount, and that cost is given in this matrix. So for example, this travel, what is the cost? So from A, if we go to B, cost is 10. From B, if we go to C, cost is 9. From C to D, cost is 9. D to A, cost is 2. So what is the total travel cost? Is 10 plus 9 plus 9 plus 2. So that is 30. Right. Now, is this the minimum cost tour? Or can there be other tour which is lesser cost? Okay, let's try one more. So from A we go to C, from C we go to B, from B we go to D, from D we go to A, right? And we have to note here that is there a path or not. So this graph is fully connected, so we'll have path in every direction from every node to every node. But if there is no path, we'll represent it with infinite. Okay. And one more thing, this graph is asymmetric. That is, if you go from A to B, the cost is 10. But if you come back from B to A, cost is 8. So this is not an undirected graph and this is a directed graph. And for whatever reason, in both direction cost is not same. So you have to be careful about that. So this tour, how much it will cost? So A to C. So this is the starting city, and start means if you are going from one city to another, this is the next city. It's representing, right? So I am starting at A going to C. So we'll take A, C. Cost is 5. Then we start at C, go to B. Cost is 6. Then we start at B and go to D. Cost is 7. And from D to A, cost is 2. So what is the total travel cost here? 5 plus 6 plus 7 plus 2. So that is 11, 18, 21. So you can see this is a lesser cost tour than this one. So like that, there can be many tours. You have to find the minimum cost tour. That is the traveling salesman problem. So input is this matrix, output is the tour and its cost, which will cost minimum. So first let us think the brute force approach. Brute force means we will evaluate all possible tours. So how many possible tours are there? So if we start at A, we can go to B or C or D. Then from B, we cannot go back to A. Remember that we can visit each city exactly once and need to come back to the starting city. So from B, we have option either C or D. From C, we have option B or D. And from D, we can go either to B or C. Then same way, if we visited ABC, only we can go to D, and from D we will go back to A. ABD, we can go to C. ACB, we can go to D. ACD, we can go to B. ADB, can go to C. ADC, we can go to B. Right? So total number of tours are 6. Right? How will get that? First level will have 3 nodes. Next level 2 nodes. Each node will have 2 children. Next level each node will have 1 children. So 3 into 2 into 1 is 6. In general, if you have n cities, how many tour will be there? N minus 1 factorial. So which is exponential. Fine. Okay. So let us see how we'll solve it with branch and bound. So for branch and bound, you require a lower bound and an upper bound. Lower bound will tell you that the solution will cost at least this much or more. So it will give you an idea or a bound that in the solution cost, right? And the upper bound will tell you that what is the best cost solution we have found so far. So let us see how we can calculate the lower bound for traveling salesman problem here. So the lower bound will be calculating like this. This is the unavoidable cost. For that, what we will do? We will take the row minimum. For every row, what is the minimum cost? Right? So for example, here minimum is 3, here minimum is 7, minimum is 1, minimum is 2. And then we'll subtract this minimum from the each row. That we'll call as row reduction. Okay. So for example, if we, let me write it down here. If we subtract, what we'll get? So infinite will remain same. From every value, we'll subtract 3. So we'll get 7 to 0. From every value, we'll subtract 7. So we'll get 1. Infinite will remain same. 2, 0. Then 1, if we subtract 0, 5, infinite, 8. 0, 1, 6, infinite. This we are calling as row reduction. And we'll note down this reduction cost. So far how much we have reduced? 3 plus 7 plus 1 plus 2 in row. Right? After that we'll do column reduction. We have to do both. So like for every row we have found minimum. Now in the row reduced matrix, for every column we have to find the minimum. So here minimum is 0, minimum is 1, minimum is 2, minimum is 0. And then we'll subtract these also from the column. So if we subtract 1 from the column, what we'll get? This will become 6, this will become 4, this will become 0. And if we subtract 2 here, it will be 0, 0, 4. Right? And then we'll note down how much we reduced. 0 plus 1 plus 2 plus 0. So total reduction is here 10, 11, 13, 14, 16. Okay. So to calculate the lower bound, first we'll take the parent matrix. Right now we don't have any, we have the original matrix only, so we'll consider that as a parent matrix. And then we'll apply row reduction, we'll apply column reduction. and we note down the reduction values, and this will be using to calculate the lower bound. Now what is the lower bound cost? Is equal to lower bound of the parent. Then if you are moving from parent to child, there will be age cost. Okay, so if you go from A to B, you have to take the age cost. Okay, in the reduced matrix. So here like say A to B, this will be 6. If you are going, right now we are not going here in the top, and then the reduction cost. So remember this, to calculate the lower bound, we have to add 3 costs: lower bound of the parent, age cost from the reduced matrix, parent reduced matrix, and the reduction cost. Okay. And what we will use as upper bound? Upper bound will be using similarly whatever the best solution found so far. That is the least cost, right? Okay. So let us use this lower bound and upper bound to apply branch and bound search on the traveling salesman problem. Fine. So starting here, original matrix given. For every row minimum already you have seen 3, 7, 1, 2. So row reduction is 13, and we got the row reduced matrix. Then we'll take the row reduced matrix and do the column reduction. Column reduction is here 0, 1, 2, 0. So column reduction is 1 plus 2, 3. So total reduction is 13 plus 3, 16. And we have this reduced matrix. Okay. Now this is the start node. Next we'll consider the edges. So we are starting from A. So we have 3 possibilities. We can go to B from city A, or we can go to C, or we can go to D. Now for this we have calculated lower bound is 16. Okay. Because parent was 0 and there will be no age cost. Now for each of these we have to calculate the lower bound. Okay. Where parent lower bound will be used as 16 and we will be using the age cost. So we will come to that. Before that, let us calculate the, as we discussed here, reduction cost. Okay. So first let us do the reduction cost for A to B. So when you want to calculate the reduction cost, first of all, you have to take the parent matrix. So we'll take this matrix. We are calculating A to B, right? Then we have to set row A as infinite. All the values will set here to infinite. Column B. So column B, everything will set to infinite, and the age B to A. So we cannot go back from B to A. So BA, this we have to set as infinite. Remaining value from the parent will copy or will remain same. So what is the matrix we will get? Is this one. Row A set to infinite, column B is set to infinite, and the reverse edge is set to infinite. B to A is set to infinite. Remaining we have copied from parent. You can see 0, 0, 0 infinite 4, 0 8 infinite, 0 0 0 infinite 4, 0 8 infinite. Okay. Okay. So when you are calculating the reduction for a node, first thing you have to prepare this modified matrix from the parent reduced matrix. Okay. Now on this we'll try to apply the reduction. So how much we can reduce in row? So here all are infinite, we cannot reduce anything. This one is 0, 0, 0. So row reduction is 0. Now in column if we look at 0, here all infinite, we cannot reduce, 0, 0. So total reduction cost will be 0. Right. Now we'll calculate the lower bound for this node. How much it will be? Parent lower bound was 16. Reduction cost is 0. Now we'll check the cost of the edge A to B in the parent matrix. So A to B in the parent matrix, how much it was? A, B, cost is 6. So we'll get 16 plus 6 plus 0, total is 22. This way we'll calculate lower bound for every node. So lower bound here we got 22. Next we'll calculate lower bound for this also, C, A to C. Okay, same approach, A to C. We set row A as infinite, column C as infinite, C to A as infinite, remaining we copied from the parent and we get this matrix. Now let us try to reduce here. Can we reduce anything? Here row 0, here 4. So we can reduce 4, this one is 0. So we can do row reduction. So if we do row reduction, we will get infinite 0, infinite 4. Now if we want to apply column reduction, this is 0, 0, 0. So in column we cannot reduce anything. In row we reduced 4. So total cost will be parent lower bound 16, reduction is 4 and the edge cost. Let us look again at the parent matrix. A to C. A to C, edge cost is 0. So total will be 16 plus 0 plus 4, 20. Right. So for the next node, lower bound is 20. Same way we will calculate the lower bound for D node. A to D. Again set row A to infinite, column D to infinite and D to A to infinite. Remaining value we have copied. Now can we reduce anything here? Here minimum is 0, minimum is 0, minimum is 0. So nothing to reduce in row. In column 0, 0, 0. So no reduction. Reduction cost is 0. Next we have, so here lower bound, how we will calculate? Parent lower bound is 16. Reduction cost is 0. And next we have to look at the edge cost. A to D in the parent matrix. So A to D, and there is a mistake actually. If we look at the previous one, it was 0. So this should be 0. Right. So A to D will cost 0 in the parent matrix. So we'll put that here, A to D. So total cost is 16. Right. So we got here lower bound 16. Upper bound we set to infinite. Still we have not reached the leaf node, so upper bound will remain infinite. Next, which node will pick up? So we have 3 nodes, cost 22, 20, 16. So we will pick up node D because it is the least cost. And then from D, how many options we will have? We can go from D to either B or we can go to C. So we will evaluate both lower bound for B and lower bound for C. Okay, next we will calculate for B. Right. So D to B, parent is here D, and so we will take the parent matrix. This was the parent matrix D. Right, parents reduced matrix. And here we have to set D to B, means this will set to infinite, B column will set to infinite, remaining values will copy. So we can see that D row is set to infinite, B column is set to infinite, and B to D, this is set to infinite. Remaining values we have copied from the parent matrix. Then what we have to do next? Same thing, we will try to perform reduction. So can we reduce anything here? Minimum is 0 in row, this row also 0. So row reduction 0, column 0, 0. So column reduction also 0. So total lower bound how much? Parent. What was the parent lower bound for D? Parent lower bound was 16. So parent lower bound 16, reduction is 0, and we have to look at the edge cost D to B in parent reduced matrix. So parent reduced matrix means this one. D to B, edge cost is 0. So we'll take that as 0. So total lower bound is 16. Right. Same way we'll do from D to C. So again take the same matrix, parent matrix from D, set B row as infinite, C column as infinite, and C to D as infinite. Remaining values you have copied, and we'll try to reduce. So can we reduce anything here? Yes, this row minimum is 1. So we can perform row reduction. So if you reduce 1, you will get 0, infinite, infinite, like that. And then after that we can reduce this column 4. So this is the reduced matrix, and in row we reduced 1, in column we reduced 4. Total reduction is 4 plus 1, 5. So what is the total cost? Parent matrix, parent node D, lower bound was 16, reduction is 5. Now check the edge cost D to C in parent. So this is the parent D to C. Cost is 4. So edge cost is 4. Total cost is 25. Right? Fine. So we got lower bound. So total how many? So far we got here lower bound, we got 16. For this we got 25. So next which node will pick up? We have 3 live nodes, 22, 20 or 4 nodes, 16, 25. So we'll pick up B, right? Then from B what option we have? From B we can go to A, D and B completed, only remaining is C. So next we'll calculate B to C. B to C. Right. So we'll take the parent. Sorry. This is the parent. D to B was taken, parent. Here from B we'll go to C. So same thing. In the parent matrix we'll set B row as infinite, C column as infinite, and C to B is infinite. Remaining values we have copied. Next we'll apply reduction 0, 0, no reduction. So total reduction cost is 0. So at parent what was the lower bound? B lower bound was 16. So we took 16, reduction is 0, and edge cost B to C in the parent reduced matrix. B to C, what is the cost here? B to C cost is 0. So cost will be 0. Total cost is 16. Right? So you got this lower bound also. So let me draw the tree. We started with A. What was the lower bound? We calculated 16. Then from A we had 3 options, B, C or D. For every node, what was the lower bound? Let us look at quickly. It was 22, 20 and 16. Right. So lower bound 22, lower bound 20, lower bound 16. And upper bound is set to infinite. Right. Next we picked up this node D. From D we had two options. Either we can go to B or we can go to C. Again we calculated lower bound for both, and what we got is here you can see 16 and 25, right? So lower bound is 16 and 25. Next we picked up minimum of these are B, so we picked up B, and from B we can go to C, right? Where what we got the lower bound? Lower bound again for C, B to C we got 16. So this also will set to 16. Now this is the leaf node, and this cost is less than the current upper bound, so we'll update it to 16, right? So this is completed. Next, which node will pick up? Next, whatever node remaining live nodes cost are more than the current upper bound. So remaining nodes are costing 22, 20, 25, which are greater than the upper bound. So we'll prune all the nodes, and we got our solution. Search is completed. No more nodes remaining to explore. We got the solution. What is the solution? A to D, D to B, B to C, C to A. Right. This is our tour. And what is the tour cost? If we go back to the original matrix, yeah, let us draw here. The tour we got A to D, D to B, B to C, C to A. A to D, what is the cost? 3. D to B, cost is 3. B to C, cost is 9. C to A, cost is 1. So total cost is how much? 3 plus 3 plus 9 plus 1. So that is 16, right? And you can see that we found the solution. The cost is 16. Fine. So this was traveling salesman problem. If we apply brute force, complexity is going to be order of n factorial. By using branch and bound, we reduce the search space. We use lower bound to prune the nodes, right? And remember, worst case still can be exponential here. Okay. And if you get a better bound, you will get more pruning. If pruning is more, performance will be improved. Fine. So this will complete the topic of branch and bound. So this is a general technique for optimization problem. Here we explore the state space using bound, and we prune suboptimal solution as early as possible to improve the cost, searching cost. Okay. And this can be applied to different problem like TSP, job assignment, and then you can apply it to 0-1 knapsack. Thank you.